Welcome back. Now we're going to start exploring the physiology of the cardiovascular system. And to do that, we're going to start with pressure. So by pressure, what we mean is what amount of force is being exerted. And we measure that in humans in millimeters of mercury, which is how blood pressure cuffs work. So generally, when we're talking about blood flow, we're talking a volume of blood that is moving from place A to place B. And so we would measure that in milliliters per minute, how much. So we can use how much is moved at any one time and then multiply it to how many times that happens in a minute in order to determine how many milliliters happen in a minute. And this is going to be dependent on two different factors. The first factor has to do with the blood pressure in the blood vessel. And it's not really what is the blood pressure we're measuring at one point, but rather what is the difference between the two ends of the blood vessels. For instance, what we will be seeing is when the blood pressure is higher, then the speed of blood flow is going to be higher. And I'll go in more details on the next slide. And the second factor which affects blood flow has to do with resistance to blood flow. And there's this very complicated equation here, which you don't need to memorize, okay? There's other equations you know, this is not one of them, but you do need to understand what's going into this and whether they are proportional or inversely proportional. So the capital R, resistance, basically is looking at three different things. What is proportional to it has to do with the blood viscosity as well as how long that blood vessel is. And then what's going to be inversely proportional, in other words, be as it goes up, resistance goes down, and vice versa. And that has to do with the radius of the blood vessel. So let's look at these factors a little closer. And in order to do that, I need to define that term resistance. So resistance has to do with the friction between 2 points. That friction is what is impeding the blood from flowing, okay? So most of you have cooked on frying pans before, so you know if you have a non-stick skillet, there's no resistance. You can fry your egg and it slides right onto your pan. But if you're using a regular frying pan, you have to have some kind of oil or something to create a barrier for your egg in order to be able to be removed, or else it'll completely stick to the pan. So the resistance in a blood vessel is going to depend on three different factors. The first has to do with the lumen of the diameter. And it doesn't matter why, but the smaller the lumen is, the greater the resistance. So if we have nervous stimulation, which causes vasoconstriction, and the diameter decreases, then we know the resistance is increasing. Also occurs if you just have atherosclerosis, decreasing the radius. The second factor has to do with the viscosity of the blood. And the viscosity, if you recall how we measured this, is by looking at the hematocrit. So the higher the hematocrit is, once you're at the upper levels of normal or higher, the greater the resistance. And the lower the hematocrit is in the bottom range of normal and lower, the less the resistance. And then the third factor has to do with the total blood vessel length. And that just is a matter of time that the blood is in contact with the blood vessel wall. And so the blood vessel has more of an input on it. So as you grow, your blood vessels grow longer. The same thing if you just put on weight rather than just going from childhood to adulthood. But as an adult, if you go from 150 pounds to 300 pounds, that means your blood vessels have to get longer to get through all the adipose tissue. So the total vessel length would increase, and so that would increase the resistance. Now, when we're doing measurements on a person in a clinical scenario, obviously they're not growing during that part of the day. So we don't and we are not going to consider the total vessel length in our calculations, although it is a factor. So generally, looking at diameter versus viscosity, the diameter change has a much more significant influence on resistance than the viscosity does. So here's a question, pause it, and see if you can figure out the answer before you continue on. All right, so now let's talk about some changes in blood flow, because that was another big factor. And for blood flow changes, we're looking at changes in pressures as well as changes in the diameter of the blood vessel. So let's talk about pressures first. And for changes in pressure, we're looking, what is the pressure at the beginning of this vessel versus the pressure at the end? So the top example is showing a blood vessel that starts with a pressure of 50 and ends with a pressure of 10. So the net change is 40 millimeters of mercury. And so that would have a certain amount of blood flow. Whereas the bottom blood vessel is showing that it's starting higher at 90 and it's ending at the same point at 10. And so there's a much bigger drop in blood pressure, thereby the change in this example is twice as much, making the flow twice as much. Now we could have, instead of making the ending points the same, made the starting points the same, where both were starting at 90 and the first one was ending at 50 and the second one was ending at 10. So it doesn't have anything to do with the fact that where you're starting on a systolic pressure versus where you're going in a diastolic pressure. It has to do with what is the net change in pressure. So the net takeaway from this is, if pressure difference increases, then flow increases. So now let's look at vessel diameter. In this one, between vessel 1 and vessel 2, we have doubled the radius. And if you go back to that initial equation way back here, you can see the radius is to the power of 4. And so that is how I clearly can make the statement that by doubling the radius, we have the resistance changing by 1/16. So the flow increases by 16. So the net takeaway from this is, if pressures are staying the same, but increase in resistance occurs, as in the vessels getting smaller, then flow decreases. So to increase blood flow, we want to either increase the blood pressure difference or decrease the resistance to flow by increasing the radius. All right. So here's another question for you to answer, and this one's actually multiple choice, so go ahead and pause it and figure this one out. And so that brings me to the last point for this section, the relationship between flow and pressure. So pressure is flow multiplied by resistance. So if pressure is flow times resistance, then blood flow, which is what we're really looking to figure out, is pressure divided by that resistance. Okay. And so now I've got a couple more questions for you. So go ahead and pause them, figure out the answers, and then I want to thank you. That's it for this section, and I will see you as we continue our exploration of cardiovascular physiology.